Yeah, right after the talk, there will be wine.
Yeah, I can say that.
Yeah. Today we have Amihay Hanany, and he's going to talk about Quiver Subtraction on the Coulomb branch.
Thank you very much. I'm going to talk about the Coulomb branch. It has the potential to have connection to cluster algebras. I don't know. It's a big challenge to try and find. Is to explain what it show some examples, and those two things that we are to find connection. The Coulomb branch is some in the sense that our hyperkähler quotients related to equipoise algebra. Connection between hyperkähler quotients and Coulomb branches and try to go through this set of connections. We'll give the so it's been a real challenge to define the notion of Coulomb branch to mathematicians. And this became a work by Nakajima and his collaborators in to give this definition because I'm a physicist, not a mathematician. And I also found that people which are not so much in representation theory, even representation theory, find it hard to understand his definition. So I certainly won't make an attempt to do that. Instead, what I will show that I presented to Nakajima led him to. This is called the monopole formula. So let me start with the input. So this is a collection of a difference what we do and what cluster algebra people do. Essential data in order to this
From that you don't have errors.
and we don't have arrows, so we in fact we abuse the name, we call it Quiver, but in fact
Privately they do, they just don't tell you. Privately they do, they just don't tell you what they are.
with oriented quivers.
Or maybe there is a
B and
protective
quiz
algebra.
Who is
With algebra.
so right, so the so those groups we will take them to be GL K1 up to GL Kn. This is going to be G by the edges. R will be let me put them like that. So I'm going to associate the vector space. With edge. Going to use it. For the structure, the hypercare quotient, this data is not so necessary for the construction of the Coulomb bind. So let me not get into that because time and
And the same for N. Just not.
another.
So you also have two matrices for frozen and non-frozen edges.
Yeah, but soon I will. So since I want
There are no
to
frozen edges. There are no frozen edges.
Okay, yeah.
Oh, you said frozen edges.
Yeah, I mean edges between frozen by
Oh,
matrices.
here. Yeah,
Yeah,
no, I don't have it.
Yeah.
Matrices. Yeah, we take them to be complex valued, but again, if we would have time, I will explain what is the hypercare quotient and how we deal with it. For Coulomb branch, we don't really use this, so let's not get into this thing. The detail of the R, so the choice of the representation is now going to be just the fundamental representation. The fundamental representation. I'm going to need Langland's dual lattice.
Fundamental, you mean adjoint?
No, the one which has dimension k.
Defining.
it's called defining. So in physics, we use different names to mathematics. So might be the defining, the one with linear dimension rather than quadratic.
Call it.
You could have a look at the paper. It's called towards. And yeah, if anyone can read the paper and explain. To use the Langlands dual group, which we will call G hat, and there's going to be a practice of weights. Let's call it dual. By a set of 1 up to. Actually, I'm going to need. G is a product of those guys. I'll have a product of while loops, and I want to impose to restrict to the principal chamber for GLK. So I'll put an order. The while loop is SK, so I'll just set an order on J. And here's the wonderful formula. I'm going to take a variable t, take the sum over all in the dual lattice. And chamber. This variable t will by power delta of m 2 times delta of m, where I give you delta of m soon. More formula, and soon I'll explain what it does. So delta m of t. Here comes the reason why I need a group representation. We will have two contributions, one associated to representation. It's going to have some, since these are co-weight, there is natural pairing with weights boots. Call it weight. Possible rules. That's the only thing I need for the presentation. These matrices, you could forget about these things. It's good for the hypercale quotients, but not.
W in R.
Yeah, so I take, so since I have the representation, so it's going to be the fundamental or the defining representation under the weights of the representation. So let's be explicit. If I have a node like that,
Highest,
so
highest.
no, I need to go over all weights in the representation. So so let's be explicit, and let's say that I have an edge like that, and it has label k prime. So I need to assign the coordinates on the dual lattice. So I will have integer numbers m for the first node, and m1 prime up to mk prime for the second node. So this contribution here will just be a sum of absolute values. All m over all m prime the final representation result of the first L in M prime is the result. If I have a frozen, for simplicity, I just set all of those. I'll get some expressions with one present. So I know how to construct the function delta for all of these. For the case of alpha, again, very simple because alphas are roots. It's just going to be a difference of m's type, right? And I have to
minus what? Alpha in G.
no minus 1/2. Plus 1/2. Here,
Yeah.
okay. So here minus 1/2, the sum over all roots of the algebra, and the
G is
pairing.
now roots, not the group.
So that's so I need the group and I need the relation.
Alpha in G means the same as W in R. Roots of G.
Yes. Lambda.
Yeah.
And m's are in the dual.
M's are in the two, yeah.
This. And once we provide this, I'll get the so-called numerical formula good for computing function Hilbert series for any.
Hilbert series of what?
Yeah, so we get to that. Let me just finish to tell you what is P.
Yeah.
Then I will. Need M. Let me put it here. Stabilizer. Means that if I'm on the boundaries of the while chamber, the stabilizer will be bigger. In general, it will be just C star to the power of the node there. Them are different, then the stabilizer is just a star. But if some of them become equal, and the stabilizer is them which are
What does it play in?
the M's are all in C. The highest weights because we're still the principal Weil chamber, but they will be in a dual lattice. Remember that they are in a dual lattice.
Lattice is Z to the K. Is that what?
There is a Z to the K, and there is a action of the Weil group from Z to the K, and you could highest weight for a long dual group, but it's not going to be too. So yeah, so I have this stabilizer. So it's just a product of GLs, depending on the partition, on the way those guys are equal to each other, and so HM has Casimir. So HM has degrees, Casimir invariance. Up to K. Right, so if I'm in the bulk of the Weil chamber, or the stabilizer is just the product of stars, and so each C star has a Casimir invariant of degree 1, and so all of the D's are 1. But if I'm in the boundaries, the D's begin to go higher, depending on the value of K. And so, and now I can define P M of T. Just the product I up to K, 1 over 1 minus T to the 2 bi. Okay, so now we have the formula, and I need to tell you what is the Hilbert series. So since this is the Coulomb branch is a symplectic singularity, it has holomorphic functions. And what the Hilbert series does, the Hilbert series counts the degree of T. The multiple formula for this quiver, 1 and n. We can go over all of those ingredients, and I will find that the Hilbert series 1 minus T to the n. To n, 1 minus T to the n. Squared. The Coulomb branch, instead of saying the Coulomb branch, I'll just denote it by C.
Right. How we can.
Algebraic variety. This is an algebraic Poisson variety. This is a
Let me give you the example. So
variety.
for C2,
Complex complexity.
Yes.
for C2, let's see what is the Hilbert series for C2. For C2,
C2.
I have two
Polynomial ring in
variables,
two variables.
Z1, Z2,
Poisson.
right?
Graded.
And a holomorphic function will just be Z1 to the K1, Z2 to the K2. So if I take K1 and K2 to be all of the non-negative integers, then that's the set of all possible holomorphic functions on C2. And if I just collect all of them and sum them up, I'll give weight T to the K1 plus K2, that's the function. Then I'll get the Hilbert series to be 1 minus T squared. Okay. For C2 mod 10, what I need to do is to take all of the holomorphic functions of C2, the functions which don't satisfy, which are non-trivial under Zn, only keep those which are trivial under Zn. The Zn action is the usual Zn action. C1 going equivalent to
We don't know any functions other than holomorphic functions. This just means functions, algebraic functions. Polynomial
I was
functions
just wondering
on
why
C2.
you take quotient by D.
quotient by gauge group. The Coulomb branch is not a quotient by gauge. Following quotient, over here by definitions, right? That's the reason I didn't need. So when we were, this was a distraction. These matrices use them for constructing the Higgs branch.
So you have black box, and on this black box there are some holomorphic functions, and count this holomorphic function by this formula. This is what we have.
And that's the Coulomb branch. And now I can use the symplectic geometry and the Hilbert series to cover what this variety is. And it becomes very interesting. Another thing that I will need is the following. So let's take an n-1 quiver. All nodes are 1, and frozen nodes on the first and the last. And I'm now going to put this into this black box with all of the ingredients and compute. What I will find the Hilbert series is going to be a sum from K 0 to infinity, and here I'll put the representation with highest sum. Sorry. the highest root of the GLN. Is enough, and K theta is the representation that has highest root equal to K times theta. And this actually tells us that the Coulomb branch equivalent orbit of SLN. Exercise, given the data I have over here, I plug the numbers, compute. I need to check that it's not trivial that the multiplicities of the powers of t are dimensions of irreducible representation. Orbit of high school. An algebraic description, maybe this is better for this audience. So the closure of the minimal important orbit is the set of the trace of m equals to 0, m squared equals to 0, and rank of m
on the left-hand side? Or is it finding the Hilbert?
I gave you the Hilbert series.
Okay, that's the definition.
Yes. The Hilbert series, Nakajima gives the definition.
The theory, Coulomb branch is Coulomb branch is a graded Poisson algebra. Is how you compute the Hilbert series. So you how to compute algebra, just tells you how to compute the Hilbert series. It's Poisson algebra.
Yes, it is. It is always a Poisson algebra.
And you have some idea of what the Poissons.
In simple cases, we know how to do it.
So the relations kind of it's kind of guessable in simple situations what this Poisson algebra must be.
The whole class of examples and got very complicated spaces just because. So this really is a very useful formula. The way we think about Coulomb branches, we managed to find the exact Coulomb branches by this information, which is. So we didn't know how to do. I'm not aware of anyone which knew how to do.
Perhaps
Next thing, yeah.
can you write down the quiver for the closure of the minimal Hilbert orbit of V6?
Yeah. Is the minimal that I gave over here. I can compute the Hilbert series. Actually, the same formula, exactly the same formula, except that theta would be the highest root of E6. And that's it. The rest just.
Do you know, I mean, do you know the Coulomb, how confident are you the Coulomb branch is this variety?
Well, here you could use other techniques, and that's quite confident. And you know, using Nakajima's definition, he confirmed this, right? So
Nakajima's definition is
yeah, so he works with the affine Grassmannian. So we need
Okay.
to know the affine Grassmannian. There are convolutions of the affine Grassmannian. You need to compute homologies.
oh, I see.
And then the cohomologies are roughly giving you those numbers.
Okay.
Over here. And yeah, and by this, those convolutions of homologies of convolution, he
Logical whole algebra.
Right. I see.
can in this, I won't be able to do it.
Also, cohomological whole algebra. It's somehow the algebra, not the state. Some sort of whole algebra type construction that has a Poisson structure, grading. Whether that's the algebra. I mean,
About the confidence about the Coulomb branch, I think by now there's been of tests.
well, I mean, does produce this variety, does
Yes.
produce this algebra.
Not formula, it has a definition.
The definition.
Has produced this variety. And it produces all of the Sloterdijk slices, nilpotent orbits, and it also goes beyond nilpotent orbits. So we are really Nakajima does. Space, we go to the physicists, we ask them what it is, and they give us, so the information we are able to give is of this type. Yes, and then he is able to check that this is indeed correct, right? So
Why do you have
think of it as the circular quiver.
It's the coefficients of the sum from
And-
the maximal roots, right?
Yes, yes,
With
yes.
one box.
That's right. That's
Yeah.
right. You need two of them, right? The maximal root for A only, combination of.
One box.
Start with this. All of them are one. Then there is an operation which allows you to freeze one node of one without any cost in the computation. So if I take this and I freeze this, then I get the four nodes. And one here and one. Similarly, I can do for E6. I take a fine E6.
Why
And
two
I can
boxes?
pick one of the three. once, list them,
And A is going to be distracted.
and
That's the question.
why can
Why two
you do
boxes?
that? What?
How do you have two boxes?
Because it's connected to this and this.
It's frozen, it's brittle.
So, yeah, I mean, is that a surprise?
Of the adjacent one should be twice the local value.
That's a good.
And
That's a
the-
good.
We don't require this, the frozen ones, so frozen twice to
I see. Wait. Let me say it in this way. It's a simple graph theoretic statement. Every quiver that I get, which contains no frozen nodes, allowed to take one of the nodes, which is 1, and freeze it. And this will be at no cost to the model.
If it's connected to several vertices, you're allowed
Then
to,
all of them will get a frozen configuration.
you're allowed to break the node up into pieces so that
Yeah.
it's not connected to more than one.
If I'll have such a configuration,
The input is the same group, it's the same representation.
then this is the same as K1. Trying to avoid this thing because it is a potentially.
They have the same numbers, right?
You don't have to have the same number.
Subtraction. So the next thing we want to understand is the singularity structure. These are singular varieties, and they have points of degenerations where it becomes less singular until I get to the origin, where I guess you should say it becomes more and more singular until I approach this singularity structure using a Fawcett diagram, Hasse diagram. Means nodes, edges. Nodes are representing symplectic leaves. Are minimal language familiar, probably not. Geometers. Let me give an example. If I take this do several examples. To n points. Numbers here for the what it tells me. So if I take the singularity C2 mod Zn, there are two regions. Is the origin, which is the singular point, and then every other point is a point that I could get by doing an action with the. I have a Poisson bracket. I could get from any point to all the other points. So that's the notion of a symplectic leaf. And so in a symplectic leaf, I'm able to move along of the points of the leaf one to another by better than what I mean. So that's a symplectic leaf, and the transfer slice is telling me what kind of parameters do I need to tune in order to move from one leaf to another. So it's always conical, and in this case, it's just the singularity itself. C2 mod. Let's use a notation. This is a notation which was introduced by the an minus 1, capital A n minus 1. So that's the I did over here. That's capital A n minus 1. The minimal orbit. So I'll SLN closure has leaves the trivial, the origin, and anything else. It's in one leaf. Dimensions are 0 and 2n minus 2 n minus 2. The line is the closure, and so let me take another example. So you see that when we wrote the minimal nilpotent orbit, we insisted that the rank is at most 1 for the minimal orbit. If I instead relax this condition and allow for an integer k instead of 1, then I'll get the Hasse diagram. This for orbit is the set of zero rank of M. With zero, I won't put the dimensions. Well, maybe I put the dimension at the top. It's going to be each slice is going to be a n minus 1 at the lowest one, and then it goes up by 2. It goes up by 2. A n a that's the Hasse diagram, and I'm going to show using the Quiver subtraction how I derive this diagram. Let me explain. How should I understand this point? So since I allow the rank to be at most k, I can have k plus 1 different values. The rank can be either 0, or 1, or 2, or anything up to k. And each one of them forms a leaf. If I have a rank of a matrix to be fixed integer, and I apply conjugation on the matrix, I'm not going to change the rank of the matrix. And that's the idea of forming a symplectic leaf. I have infinitely many matrices which satisfy this condition. And so this space is stratified into sectors where there is the rank 0 case, the rank 1, the rank 2, and so on. K plus 1 such points. This is what the Hasse diagram tells me. There is the development of singularities, and it becomes the most singular as I go to the origin. And furthermore, if I want to move from a rank k matrix to a rank k minus 1, I need to tune some of the parameters so that the rank will go down. So I have to tune them. And the nice thing about it is that they form a singularity, which is one of those singularities that we introduced over here. Either this one or by Krafft and Prochenzi, which said that all of the a large class of quivers is either of type capital A or lowercase a. So let's do this and then we will finish. So the Coulomb branch one, 2, and it goes up to k. Then it remains k. Now it goes down, k minus 1, all the way down to 2 and 1, and such that the number of such nodes is n minus 1. One here, one here. I gave you the quiver, I gave you the formula for the Coulomb branch. You could plug this in, compute, and what you will find is that the Coulomb branch is the orbit 2k 1 n minus 2k closure in trivial result. And Alistair, you could ask whether how confident I am in this thing. So it's again the same answer. So now I can use Quiver subtraction. So in Quiver subtraction, what I do is I find subquiver which is either 1n1 with framing 1 like that. Let's put a prime. Balance, I did not say what is balance, but Matthew was saying the balance in his explanation when he was talking about sum of neighbors twice the node number. So you notice that these nodes have a very special property. If I sum over the neighbors of each node, it's exactly twice the node number of those nodes. So let's do it here. 1 has only one neighbor, 2, which is twice 1. 2 has 2 neighbors, 1 and 3. The sum is 4, which is twice 2. Right? So it's called the balanced node. Let's do K. Has one neighbor K on here, this side, another neighbor K minus 1 on this side, and another neighbor 1. The sum is 2K, which is twice K. So it's again a balanced node. And in fact, all of these nodes are balanced. For the physics, it's very important. It says that the symmetry which acts on the Coulomb branch is of type SLN, right? Because this is the Dynkin diagram. The set of balanced nodes form the Dynkin diagram of type AN minus 1. So, so part of the prescription for the subtraction is that I rebalance the gauge nodes, namely that I want to preserve the balance before subtraction and after the subtraction. I want that the balance will be maintained. So let's think on an example.
A really silly remark. So you would have no frozen vertices in between the two limit cases.
I'll have to change the frozen vertices such that all nodes have the same balance they had before.
But in the original Quiver, you only have 2 frozen vertices.
That's right. So let's do an example. Let's take this case here. 1, 2, 2, 2, and 1. Let's put a frozen one here, and a frozen one here. So first of all, it's of the type of the quiver that I have over here. For K equals to 2, and N is equal to quiver of type, the second type, right? It's A3, right? It's an A3 quiver, 1, 1, 1, and 1 here, 1, right? That's this guy. Okay, so let's subtract it. If I subtract, I find this one stays, right? So let's subtract 1, 1, 1, 1 frame here, and here. Then I get 1 in all of them. This one was balanced, so balance is good. However, this one has changed its balance. It was balanced here. Now it's no longer balanced. So I need to add a framing and one here because it's symmetric. That's the process of the Quiver subtraction. And then I just repeat. Until done. Started with a modular space which has dimension. I didn't tell you, so let me tell you now. The dimension of the Coulomb branch is the sum of gauge nodes times 2. So in this case, it's 2 plus 2 plus 2, 6, plus 1 plus 1, 8 times 2, dimension 16. I subtract in A3, this is A3, dimension 6. Did I say that? I think I said it. -1 has n minus 1 nodes of 1. The dimension is 2 n minus 1. So I subtract an A3. Now I repeat. So this is a Quiver A5. And if I subtract it, I'll just get nothing. When I'm done with the process, subtract A5, and I end up with a 0-dimensional object. So I recovered the Hasse diagram for the O2 1 6 minus 4 is 2 closure of SL, which is what we said over here. Description that we have, we can now apply and understand the singularity structure of a whole range of Coulomb branches. And all of them will be of this type, right? Will be of type finite A and with thousand nodes attached to them. What we got here was a prescription to take any such quiver, compute the Hilbert series for the Coulomb branch of this quiver, and we saw an algorithm to compute the singularity structure using Hasse diagram. The big challenge is to try and figure out how is this related to cluster algebras. I mean, now it's just a collection of games to play.
Thank you very much
Thank
for
you.
your talk. Are there any questions?
Yeah.
So how do you predict the stratification without knowing the actual variety over the space? What the actual space is? Only knowing the Hilbert or other information you can.
Stratification, no. The way in physics we derived it was to use a physical embedding, which I did not talk about, which simulates this. In him talk about an algorithm for stratification. It does think about stratifications, but I think he would agree with the results of the computation. But I haven't tested with him if he agrees to the algorithm.
present.
that I presented over here. Yeah, we, in case of other algebras, D-type and also for non-simply laced, we could extend it, but we will have to introduce more ingredients of the objects that we subtract. Here I gave you only 2 objects that we can subtract, but more generally, there will be a whole collection of my questions when I came here was to test all of those results for the stratification using some other techniques. Right? So we could think of it as a conjecture. These guys, they can be thought as so the Coulomb branches could be thought as slices in the affine glass magma. For this, there is a work by representation theorists, Kamnitzer, Webster, and more there is Oded, some, and they actually computed the slices and the stratification and fully agrees with we generate conjectures, but it's some nice challenge conjectures to play with.
Cluster algebra, and I can see it's as we're phrasing vertices. Is that the reasoning, or why do you suggest that there should be a relation?
It's from the initial point. So projective algebras are discussed in quite a lot of detail, and they are related to hyperkähler quotients, and we call hyperkähler quotients Higgs functions. There is some special duality, which I said over here, 3D mirror symmetry, which relates Higgs functions to Coulomb functions. There is a pair of quivers, like this pair, the pair here. This one and this one have a very interesting property that the Higgs branch of this us about some cluster algebra through the pre-projective algebra. I do it through this Higgs branch, but can I do it through the Coulomb branch? This that's the challenge, because we get away from this description, which was stuck with at the beginning, because that's the description of the Higgs branch. Right? So I no longer talk about matrices. I completely change the formulation, but yet again, I get the same objects I would get. Change a quiver, right? So can I take a quiver data and define some algebra on it, such that I will get results which are dual to what I'll get from. That's the challenge.
And could you also, I mean, other quivers, so
It should be a fine, not finite.
okay.
Yeah, that's very crucial.
D for tilde then.
So here, right, so if I take E6, it's a minimal orbit. It only has 2 points in the Hasse diagram. I cannot subtract anything further, but I also learned that E6 is one of the allowed quivers I should subtract. So if I get, but you see, this thing won't show up in this function, right? So let me give you one nice modular space. My favorite. 1, 2, 8, 4, 5, and 2. It has three leaves. Subtraction. We have an E8 and D10. Mention 0, 58. You see E8 is embedded there. Subtract it. Rebalance. You get D10. All of them are balanced.
I think it's frozen.
Except for this one. Let's put it in a different color.
Is it frozen? It's not.
Oh, it's not frozen. None are frozen.
Oh, but it's not balanced.
It's just not balanced.
Right.
Five also.
Yes, because it has two neighbors, 8 and 2. It's
Oh, yes.
which is twice.
Cool, balancing. With node values.
Three, 4. This. So we you find the Hasse diagram to be consist of 5 points corresponding to the 5 partitions of 4. Use
This by taking the pre-projective output of except projected there.
that Coulomb branch is equal to the Higgs branch.
Ah, so they exploit this fact.
They
Without
did,
knowing
yeah,
it, presumably.
without knowing what is a Coulomb branch. Yes.
Right. The thing with this becomes the modular space of quiver representations in that example is because just what that is.
And the fact that the diagram they find is symmetric. The diagram looks like this. There is an A3. This without knowing it. The paper you'll find that the diagrams will be equivalent to this one. Or say in the approach is that it translates their procedure from Young diagrams to quivers. Once I do that, I can apply it to any algebra, not just to type. They had to work quite hard to do the combinatorics for classical algebras, and they just couldn't do it for exceptionals. But our procedure over here would generalize to those cases as well. Well, it's quite a nice generalization. You know, if for very little effort, you could compute a stratification of many moduli spaces.
Yellow.
No. So the quiver is complicated because it has all of these large numbers. The dimension is very large, but the stratification structure is very simple, only 3 leaves. So I consider this as a very simple modular space. It's slightly more complicated than minimally 8 because minimally 8 has 2 leaves and this has 3 leaves. So it's just because of this.
There's still got big symmetry.
Yeah, so the number of nodes which are balanced are forming the D10 algebra. And so the symmetry acting on this variety is SO20. The leaves are, sorry, the leaves. No, they are not orbits. Well, they are orbits of SO10, if that's the question. Of SO20, yes. Yeah, there are orbits of SO20 because it acts on the whole modular space.
It acts transitively on the orbit.
Yeah, it keeps, so I can act with, so the generators of the ring transform in the adjoint of SO20. One of the spinors of SO20, natural action of SO20 on those generators, and I can, and also on each of those leaves. I have a spinor representation over there that complicates the analysis. This is the thing which makes it not a nilpotent orbit.
Because it's the spinner, but it is still orbit. It's still orbit.
It's still with the natural action of SO20. Yes. So that's the way we want to call it, orbits. There is a symmetry which acts on this space.
Is it transitive on the leaf?
Yes. Okay.
Yeah, any questions? No, during the or in person.
Yes, yes. If anyone wants to come and help carry wine and beer down, you're very welcome.
But then